Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafizan bin Azmin, 20139288. Today, we want to present our lab assignment 1. Okay, I want to talk about Microstrip Bandpass filter. What is Microstrip Bandpass filter? The bandpass filter can be used to isolate or filter out specific frequency that fall within a specific band or frequency range. The cut-off frequency or C-point of simple RC filter can be previously controlled by connecting a single resistor in series with a non-polarized capacitor in either direction. The microstrip is a type of parallel plate transmission line that consists of a single ground plane separated by a dielectric substrate and open strip conductor. Microstrip lines are the most common type of transmission line used in a microwave integrated circuit. A filter is a device substance that allows certain electric current or frequency range to pass while preventing others from passing. The filter are classified as low pass filter, high pass filter, band pass filter, and band reject filter based on the frequency they pass. Okay, that's all for me. Thank you.
Hi, my name is Muhammad Alif Aiman bin Mazlan, 2013928841, and I will present about the circuit design of a microstrip bandpass filter. As for the circuit design of microstrip bandpass filter, we have been using one resistor along with 3 inductor and 3 capacitor. The value of N is equal to 3 because there is 3 pair of inductor and capacitor. For the calculation to get the value of each component, we use the formula that has been given in note. Okay, next slide please. Okay, as we can see on the slide, to get the bandwidth value, we need FC, F1 and F2. The value of FC, F1 and F2 has been obtained by referring lab to B. After that, the value of G has been obtained by referring to the table of insertion loss maximally flat. The omega naught formula is 2 pi f and the f is referred to the FC. And the Z naught value can be obtained inside of the circuit on term 1. For the value of delta, it can be obtained by using the bandwidth value. And lastly, we set the start value to 850 MHz, the stop value to 885 MHz, and the stat value is 0.01 MHz, so that we can get the bandwidth output in between. Okay, that's all for me. Thank you.
Hello, my name is Muhammad Aiman Hakim bin Muhammad Anwar. Okay, this is the result that we get. Okay, first of all, I want to demonstrate the ADS, the circuit that we get. Okay, this is the circuit that we calculate. Okay, for the circuit, I want to this is the calculation that we using the calculation to get the output. This inductor and capacitor is same with the L2 and C2. Then L3 and C4. If we using the calculation the calculation value, we cannot get the bandwidth that bandpass that we want. So I change it to the small value to get to get the bandpass. Okay. For the tuning, I just tuning it. I just tuning it. I just tuning the term 2 to get the result, because we get actually the accurate bandpass filter using the small value of the L3 and C3. Then for for the graph, we get for the M1 is 857.8. Then for the intersection we get a XC9 for point 4. Then for the M2, eh for the M2 we get the XC5 MX9.4 millihertz. For the intersection we get the XC5.2 millihertz. We have to tuning. Okay, this is the tuning if we accurate. Tak jadi. Wait a minute. Okay. Tak jalan. This is when we the tuning is on based on the Smith chart because we want to get the Z naught 50 ohm. We tuning and then we get the value that we want. We just because the bandpass filter is already accurate. Okay. Okay. For the comparison we get that is for the lab 2 we get the upper is exceed 2.43. Then for the upper for ADS we get exceed 857.9 millihertz. Then for the lower we get 873.68 in lab 2B. Then for the lower in ADS we get exceed 9.4. Then for the intersection we get from the lab 866.06. Then for the intersection for in ADS we get exceed 5.2. The value is uh, is almost same in the lab 2B because we using the calculation that we use. Okay, that's all for me and thank you.
Today I will present about a Smith chart. What is Smith chart? The Smith chart is a tool for displaying the frequency dependent impedance of a transmission line and antenna system. Smith chart can help you better understand transmission line and how they behave in terms of impedance. Smith chart can also be used for impedance matching. Next slide. Okay, after create the circuit, we get the Smith chart, the output Smith chart. From my left, the Y is output of output of a Smith chart assignment, and from my right is let to be output Smith chart. We are comparing between two value of frequency, which is from my right, the let to be we get is 866.06353, and for the from the let assignment we get 865.5 megahertz. So the Z naught we are using is the Z naught we are using 45.723, and for the lab assignment is 50.061. In conclusion, from based on both result, we can get the instrument error is more error than software error. That's all for me.
Well, this brings to the end of our presentation. My name is Muhammad Nabil bin Baldin. My metric is number is 20139246. The conclusion for this lab is the pass frequency is the range of frequencies in which the device being tested allows signal to pass through it with minimal loss. The stop frequency is the range of frequencies in which the device blocks or attenuates signals. Insertion loss is a measure of the decrease in signal strength that occurs when the device being tested is inserted into a transmission line. It is typically expressed in decibel and is calculated by subtracting the power of the signal after it passed through the device from the power of the signal before it passed through the device. In a measurement experiment, the impedance at the first bandpass is the impedance of the device being tested over the range of frequency in which it allows signal to pass through with minimal loss. The impedance at the stop band is the impedance of the device over the range of frequencies in which it blocks or attenuates signal. So that's all from our team. Thank you.